So for this topic video, we're going to be talking about the different notations for derivatives in calculus and the notation for an integral in calculus and how we can navigate what's going on and not get lost or confused. So let's get right into it. So I'm going to say I have some function. I'm going to call it big F of x. And recall that you can often say that this is equal to y. So I'll do just that for some of these notations that are going to come up. Now let's say I want to take the first derivative. Well, one of the most common you probably see is f prime of x. That's equal to the derivative of big F. Well, since big F is y, you may also see y prime. So that's the first notation, the little that's not an asterisk, the little apostrophe, there we go. The little apostrophe which goes here, the little tick mark. That's prime notation. The other notation you may see is the d whatever your function is over d whatever your variable is. So that would look like d f of x over dx. Well, since big F of x is y, this could also be written as dy dx. Now, both of these could also be written this way. I could put the d over dx off to the side, and I could do the same thing for y as well. So both of these are Leibniz notation. That's just named after the person who did it this way. And you can see this one kind of looks more like an operator, right? Like, do the derivative of this with respect to x. Do the derivative of this with respect to x. The first one kind of looks like a fraction, right? Be really careful about reading it that way. That's not literally what's going on, but it looks like it. And so we have df dx or dy dx. So these are both Leibniz notation. Both of these are by far the most common. You're going to see this most of the time. One thing I noticed a lot in physics, though, is that they use a dot notation. So for example, the first derivative of f, they'd put a little dot over it, and that means first derivative. You could do the same thing with y dot. And that's just the first derivative of that function. And this is dot notation. Perhaps it has some fancier name. Now, what if you want to do the derivatives again? Well, for prime notation, you would just keep going. You'd have f double prime is equal to y double prime. You could have f triple prime is equal to y triple prime. Now, of course, once you get to 4, then this gets kind of unruly or unwieldy. So two things happen. Let's say we're doing fourth derivative. You'll either see people literally just write the number 4, like in our numbers. But for f, that's clear enough, because I've got a 4 nestled in there. So the fourth derivative of f. For y, suddenly that looks like y to the 4th. How am I supposed to know that's the 4th derivative of y? So this isn't used. So once your derivatives get high enough, you would be using your function to do this. You may also see people use Roman numerals, so f of 4 with respect to x. And maybe you'd see y like that. Seeing the Roman numeral would tell me that's not an exponent, but that's still pretty uncommon. Once the derivatives get higher than 3, you would go to using big F of x and not y anymore. What about for Leibniz notation? Well, for Leibniz notation, notice how if I have d dx of f or y, I can bring it in, like right there. Usually, if you're taking a derivative again, here's what you would do. Say I do the derivative with respect to x of the derivative with respect to x of f of x. Well, I would go to writing it this way. So I would say d big F of x over dx. And so if this comes in, you can think of it as far as memorizing the notation. You can almost think of it like multiplication. There's 2 of these d's up here, so it's the d squared big F of x. And there's 2 of the dx, the whole thing on the bottom, so that's dx squared. And you would read that as the second derivative of f of x with respect to x. And of course, you can substitute a y in there. Second derivative of y with respect to x. And that would just carry on for higher and higher derivatives. For dot notation, it's pretty nice. I want the second derivative. Okay, 2 dots. I want the third derivative. Okay, 3 dots. you can either write them out as a list of 3. They start getting stacked. So y, third derivative. So like for 4 dots, instead of writing out a long line of 4, I would now have a stack like this. So that one's pretty straightforward. Of course, that can get ridiculous as soon as this starts going up like that. But those are the 3 notations. Now, even though we've got, and there's more notations than these first 2 are the most common, and you will see dot notation sometimes. So there are more notations than these, but these are the big ones. These first 2, and then this third one to a lesser extent. For integrals, we actually don't have this huge amount of notations. So if you're doing an integral, big F of x would be equal to, let's say an indefinite one, would be equal to the integral of little f of x dx, where little f of x is, I'll use the dot notation for the heck of it, is big F prime, or y prime, or y dot, I should say. I said prime, but I'm using dot notation. So that's your notation for integral right there. Big F of x is equal to the integral of f of x. That's what you got. What if you want to do multiple integrals? Well, you're going to do an integral, and then you're going to do the next integral. So let's say I had f of x, little f of x, was equal to the integral of f prime. Well, since f is equal to the derivative of big F, then f prime would be equal to the second derivative of big F. Notice I'm just flipping between dots and prime notation. They all mean the same thing. That's the emphasis of this over here. These are all different notations, but they all represent the same idea of taking the derivative. So if I wanted to do these integrals, well, the integral of f prime here would just be f, but if it's an indefinite integral, in other words, if I don't have bounds here, there might be some constant there. Call it c1. So there might be some number that gets added there, because recall, when you take the derivative, the constant just goes away. So if I take the integral of this f prime here, I'm going to get f of x, but plus some constant. Now that I have this, I can do this integral up here, plus c1 dx. Now what's interesting is if I do the integral again, let me go ahead and come down here and do this. If I do this integral again, well, the integral of little f is big F. But notice I've got that c1 now. Well, if I do the integral of a constant, well, I would just get x plus c1x. Why? Because recall, if you took the derivative, you'd get big F prime, which is little f. And then if you took the derivative of this, the x would just go away and you'd have c1. So that's the integral of what's in here. And now, because it's an indefinite integral, there might be a constant there that goes away when you take the derivative. So now there's a c2, which is why I labeled this c1, because I knew that was coming. And so if you keep taking the integral, you're going to get more and more constants getting added on there, because as you take deeper derivatives, they're going to drop off. So integrals, you have to be really careful with these constants, but this is the notation you get, just this curly s. And of course, if you had values there, a to b of little f, then let's just say that this is from a to b. Then when you take this derivative, you're going to get big F, but the notation is we put a bar here. This is for definite integrals, from a to b, and so that's going to be big F of b minus big F of a. That's why you don't need a constant for definite integrals. Is notice if I put a plus c here, I'd have f of b plus c minus f of a, and I would wind up subtracting off that constant as well. So for definite integrals, you don't need a constant, and the only notational change is that your numbers go here. And for indefinite integrals, you always need a constant as you integrate. So you wind up getting more and more constants the more you keep integrating. But in spite of those two differences, that's the only notation you have for the integral, as opposed to these 3, and there are more, these 3 different notations for derivatives. So there we go. That's a general overview of the different notations of a derivative, working on being comfortable with just moving back and forth between them willy-nilly. And then this is the notation for an integral, the only one. And then what happens is you keep integrating, and you have to be careful with your constants. And that is this